Okay, thanks for the introduction, and Thomas did an excellent introduction to understand a little bit more my presentation. Okay, edible Orthoptera are a promising sustainable protein source with around 340 species, although most of the companies producing Orthoptera specialize in the production of a few species, such as Aketa domesticus, Gryllus decihilatus, Gryllus bimaculatus, Gryllus similis, and Locusta migratoria, species that are widely consumed in Asia and Africa, and some of which are already or are in the process to be approved as a novel foods in Europe. The importance of this edible insect group has led to the emergence of a market that will reach more than 500 millions in the following years. Successfully, Orthoptera production depends mainly on temperature and feed quality, with chicken feed commonly being used for crickets and fresh grasses for grasshoppers, driving up production cost. To address the high feed costs, low-cost alternative feeding substrates, such as agroalimentary byproducts and co-products, are being explored, and it has been found that partial incorporation of some specific wheat or agricultural byproducts can be used as an alternative feeding substrate to chicken feed. However, in most cases, pure or supplemented diets containing food waste, wheat, or agricultural byproducts produce crickets with a lower feed conversion ratio, survival rates, and final weights compared to the control diets. These results indicate that the high indigestible plant fiber content and low protein concentration in the tested diets decrease Orthoptera performance, despite the primary diet of wild locusts and crickets is plant-based, containing high levels of indigestible fiber, suggesting their potential adaptation to such diets. Plant fiber is not easily to digest by most animals. In insects, fiber breakdown occurs partially through endogenous enzymes. However, microorganisms are the most effective natural degraders of plant fibers. Additionally, there are other groups of symbionts, such as nitrogen waste recycling and nitrogen fixation bacteria, that enable insects to thrive on nitrogen deficient diets. Gut microbiota diversity can vary depending on the environment and the diet in which the insects live. For example, animals raised in captivity generally have less diverse gut microbiota than wild animals. And this work is based on the hypothesis that the unsuccessful attempts to incorporate side streams with a high content of plant fibers into the diet of edible orthopterans may be due to the fact that these experiments were carried out on insects bred over several generations in the lab, and it's likely that the gut microbiota responsible for the degradation of these polymers is absent or reduced due to their captivity and synthetic diets used to feed them. So the project that I was working aimed to compare, isolate, and identify plant polymer degrading, nitrogen waste recycling, nitrogen fixation bacteria from the gut of Gryllus bimaculatus, Gryllus assimilis, and Locusta migratoria from wild population and from insect production farms, which could later serve as a putative bacterial probiotics. For that, first we collect wild animals from different locations in Spain and Colombia. And also we buy these species from different companies in Europe. Then we dissect the gut, and we use the gut to analyze the good bacterium among wild and farmed crickets and locusts, and also to isolate and identify gut bacteria with the ability to hydrolyze cellulose, pectin, xylon, starch, uric acid, urea, and fixed nitrogen. And then the best bacteria that yield the best results were used to evaluate the effect of probiotic supplemented byproduct diet on Gryllus bimaculatus and Gryllus assimilis. Here we can see the results of the alpha and beta analysis between the wild and farmed Locusta migratoria. We can see here, for example, in the Shannon analysis that the farmed locusts show a lower diversity than the wild ones. The pillow eveness, that is an index that evaluate the eveness between the different microorganisms. We found that the wild locusts had a more even distribution, while farmed locusts were dominated by a few taxa. And the fate phylogenetic diversity test that analyzed the diversity in terms of taxonomic categories, we didn't find any difference between the two groups. Then the the weighted and unweighted unifrac distances. We can see here that the wild and farmed population are separated in different axes, showing that are different. And looking in more details, which genera were more abundant in each group. We found here, for example, that Weissella were more abundant in the farmed population, along with Enterococcus and Lactococcus. And in the case of the wild populations, we found that Pantoea was the genera that were more abundant in this group. Then we were able to isolate 188 bacteria from the gut of wild and farmed Locusta migratoria. From the wild population, we isolate 95 bacteria, and from the farmed 73. And in this graph, I'm showing the percentage of bacteria that were able to hydrolyze each of the components. For example, here we can see that the wild population had more ability, the bacteria from the wild population had more ability to hydrolyze pectin. And in this part of the graph, we can see here the percentage of bacteria that were able to hydrolyze 2 or more components at the same time. For example, here just the 2% of the bacteria were able to hydrolyze the 4 components at the same time, and we found Pselocymicrobium, Pantoea, Panibacillus, and in the farmed population, Serratia. And in the case of nitrogen use, we found that the wild populations had more bacteria to hydrolyze urea and also to fix nitrogen, and only 1% of the bacteria were able to hydrolyze these 3 components at the same time, and we found that were Pantoea from the wild populations and Enterobacter from the farmed populations. Those are the results from Grillus bimaculatus. The results were very similar to the Locusta migratoria. We found that there were a higher diversity in terms of piloeveness and channel in the wild populations, but we found that the farmed population had more diversity in terms of taxonomic categories than the wild populations. In this case, we found that Parabacteroides, the general Parabacteroides, had a higher abundance in the farmed populations, and previous studies showed that the Parabacteroides is very common to find it in cricket farms and also in cricket feed. So probably that's why we also found that there is a higher abundance of this group in farmed populations. In this case, we were able to isolate 199 bacteria, 184 from the wild population and 65 from the farmed populations. And again, we can see here that Pantoea were one of the genera that were able to hydrolyze the 4 components at the same time, and Bacillus and Cylomicrobium in the farmed populations. And in this case, we didn't find any bacteria that were able to hydrolyze the 3 different components at the same time. Those are the results from Grillus assimilis. In contrast to the previous results, in this case, we found that the farmed population had a higher diversity than the wild populations. In this case, again, we can see here that Pantoea were the most abundant genera in the wild population, and Enterococcus and some Lactobacillus bacteria were more abundant in the farmed populations. In this case, we were able to hydrolyze 110 bacteria, 53 from the wild population and 57 from the farmed populations. We found Klebsiella, Pantoea, and a novel genus that were able to hydrolyze 4 components at the same time. And in this case, also, we found another Pantoea. I forget to put the name here. Then, as I mentioned, fiber is difficult to digest for most animals, including crickets, and many experimental diets aimed at reducing feed costs are formulated from agri-industrial side streams, which are typically high in fiber, limiting their use and applicability. That's why in this study, we aimed to evaluate some of the isolated bacteria with the greatest probiotic potential to see if they could help improve digestion of high fiber diets. For that, an experimental diet was formulated using locally sourced agri-food co-products and byproducts with a high content of fiber. The control diet consisted in organic chicken feed, and pod diets were isoproteic and isocaloric and had a similar fat content. However, the high fiber experimental diet had a considerably higher fiber content, that is 23%, compared to a 5% of the control chicken feed. Then, based on the in vitro analysis, one bacterial strain from each insect were used to be used as a probiotic. In this case, we select Pantoea agglomerans from Cruz maculatus and a new genus of bacteria, that is the strain E45B in Gryllus assimilis. In the feeding trial, we evaluate the effect of both diet type and probiotic conditions on cricket performance. So here are some of the pictures of the place in which we did the experiments. We can see the experimental diet, how the crickets are feeding the experimental diet. And here we can see the cricket drinking the probiotic. We supplement the crickets with water, and in the water we add the bacteria. So here we have the results of the evaluation of the high fiber diet supplemented with the E45B strain in Gryllus assimilis. We observed that the presence of the probiotic E45B, whether live or autoclaved, had a negative impact on all performance variables, survival, adult emergence, and weight gain. Interesting, the best results were obtained in crickets that received no probiotic at all, but with the control at the high fiber diets. The high fiber experimental diet did improve weight gain, but only in the absence of the probiotic, and this suggests that the probiotic strain E45B under the tested conditions may not be beneficial and could even interfere with the cricket performance. In the case of Gryllus maculatus supplemented with Pantoea agglomerans, we observed a synergetic effect between the live probiotic and the high fiber diet. Together, they significantly improve weight gain and adult emergence. However, this benefit was not seen with the control diet. Neither survival nor eggs hatching rates were affected by the diet or probiotic treatments. As a conclusion, we can say that wild crickets and locusts harbor a higher diversity and more even distribution of gut bacteria compared to the farmed ones, reflecting an adaptation to their varied natural diets. A significantly higher percentage of bacteria capable of degrading plant polymer like cellulose and pectin, as well as fixing nitrogen and recycling uric acid, were found in the guts of wild insects, and the E45B strain had negative effects on the performance of Gryllus assimilis, whereas Pantoea agglomerans showed a synergistic effect with the high fiber diet and improved the performance of Gryllus maculatus.